All right, welcome back. So we spent a good amount of time talking about two features of a given problem that need to be present in order for us to use a dynamic programming approach. Those two features, just as a recap, were overlapping subproblems and then optimal substructure. What I want to do now is take a problem that exhibits those two features and solve it, first without dynamic programming, and then refactor it using dynamic programming. So that problem we're going to start with, we've already seen, the Fibonacci sequence. So this exhibits both of those features. I feel like features is the wrong term, but properties. It exhibits both those properties where we've already went over this. I used it as the example in the overlapping subproblems video. And I also briefly touched upon it in the last video when we talked about optimal substructure. It exhibits both of those features. So with that out of the way, let's write a simple solution using recursion to calculate the nth number, the nth digit in the Fibonacci sequence. So here's what we need to know, or here's what we know in order to go and implement it recursively. So for any number, let's say the fifth Fibonacci number, all we do is take the fourth Fibonacci number and add it to the third Fibonacci number. And obviously we don't know that right away. Our code won't know that. So then we need to calculate the fourth number, which is the third plus the second. And we keep going, but we have these two base cases. We know that the first digit is 1 and the second digit is 1. So we can keep recursing down until we hit the base case. Fibonacci of 1, Fibonacci of 2, both of those should return the value of 1. Otherwise, we're going to return Fibonacci of n minus 1 plus Fibonacci of n minus 2. So if you want to write this yourself, pause the video right now, play around with it, and see how it goes. This is like 90% of the work right here. You just have to translate it to code. You have to write a function definition, that sort of thing. But this is the bulk of the logic. I'm going to have a solution in like 3 seconds. 3, 2, 1. Okay, here's my solution. Not particularly beautiful, but simple enough. We define our function Fibonacci, or I just called it fib, takes a number n, and then we check, all right, here's our base case. If that number is less than or equal to 2, we could have also just said if that number is 1 or that number is 2. We don't have to work with 0 and negative numbers, but this is just a short way of writing it because if I make a long line, I have to make the code block really long, and then the font size gets really small. So I simplified it. If n is less than or equal to 2, return 1. That means we're at the first digit or the second digit. Otherwise, return fib of n minus 1 plus fib of n minus 2. So if you trust that this works as is, you can skip the rest of this video. This is basically review from the recursion section. We had a problem just like this one. There's nothing involving dynamic programming here. We are working with subproblems, right? That's sort of the basis of recursion. We need to break it down to smaller problems. We hit a base case, but this is just plain old recursion. So first, I guess I should prove that it works. So here's my snippet with it. And I execute it, and I run, let's do fib of 1 just to test it. Okay. We get 1. Fib of 2 gives us 1 as well. Fib of 3 should give us 2. Fib of 4 gives us 3. All right, fib of 5 should be 5. Fib of 6 is going to be 8, and so on. All right, so this is working. I will warn you, I wouldn't test this with really huge numbers. You'll see that things grow very quickly. So fib of 10 is 55, but once we do fib of 20, it's very large. And 30, even larger. We're actually going to come back to this in the next video and talk about the big O notation of our current implementation. And you'll see that it's a little dangerous to do like fib of 100. I would not type that right now. I did earlier and it was a huge mistake. Anyway, we'll talk about why in the next video. So this works. And instead of stepping through it in the Chrome debugger, which I think is kind of not a great experience to watch, I built a really simple animation here to show you sort of the recursive tree. So when we call fib of 5, this is the whole tree laid out, but I have these little colored dots that are going to show us things that are sort of waiting on something to be returned. So fib of 5 is going to return fib of 4 plus fib of 3. But we don't get anything back because fib of 4 needs to be returned, or we need a value there first before we can add it to fib of 3. So fib of 4 is fib of 3 plus fib of 2, but we don't know fib of 3. So then we get to fib of 2, which this time we do know a value because, as we've seen, if n is less than or equal to 2, return 1. So that's our base case. So this returns 1, and it's green. So now fib of 3 knows we're adding 1 plus fib of 1. And that's also a base case. It's 1 or 2 returns 1. So we get 1. Add it together, and that gives us a value for fib of 3, which is 2. All right, so now fib of 4 was waiting. We have 2. We add it to fib of 2. And once again, we have that base case, which returns 1. So now we have 2 and 1. We add them together, and we get 3. And that's green. So now fib of 5, the original fib of 5, now figured out what fib of 4 was, all of this. We can add it to fib of 3, which we have to figure out again. So fib of 3 is fib of 2 plus fib of 1, but we have to start here, of course. Oh, it's exhausting to talk about. This returns 1. It's a base case. So does this. They add together to return the value of 2 here. And finally, our original line, the very first time we ran fib of 5, this line has been waiting. And finally, it's actually going to return a value, 3 plus 2, which is 5. And ta-da, we're done. So that is stepping through the process. Hopefully that makes sense. If you're struggling with the recursion here, I definitely recommend you go back and review the recursion section. I know it's kind of not that exciting, but if you are struggling with it, it's going to make the next sort of couple videos a lot more challenging to understand. Not to scare anyone away. Please don't go away. Okay, so that is with plain old recursion. It's not a very good solution. It's short and compact, I'll give it that. It's a great way of teaching recursion, but it's really inefficient, and we'll see why in the next video. We're going to talk about the big O of this solution.